Alright, hello class. Today we're going to be talking about section 3.7, which is on implicit differentiation. And what implicit differentiation is it's basically just applying the chain rule when we don't know what the, say, function, that inside function happens to be. Right, so we know from the chain rule that if I take the derivative with respect to x of, say, y cubed, that this comes out to be 3y squared times the derivative of that inner function y. Okay? And that's all implicit differentiation really is using this chain rule idea with y's instead of with the sort of functions we looked at last time. Okay? And so, for example, real quick before I get into some motivation type problems, we all know how to say take this derivative, right? If I take the derivative of everything, if I have y equals x cubed plus 3x plus 5, and you take the derivative of everything, right, what we get on this side is dy over dx. We just move the y to the top. And then we get, taking the derivative of this side, 3x squared plus 3. Okay, but if I started instead with something like y cubed is equal to x cubed plus 3x plus 5. Well, again, if I wanted to take the derivative of both sides, I'll do that in this step. So the derivative with respect to x of y cubed is equal to the derivative with respect to x of x cubed plus 3x plus 5. And so this side of the equation stays the same, right? It's 3x squared plus 3. And on this side, well, we use what we know from the chain rule, that the derivative with respect to x of y cubed, note here that they don't match. From the chain rule, we have that this is 3y squared times the derivative of y. Okay, and this is essentially how implicit differentiation works. It's when you have y's in your function or in your expression as well as x's, and you have to take the derivative of everything. Right? So here's a motivating example of where this comes from, or maybe a motivating factor that we can think of. Alright, so let's start by looking at the circle centered at the origin with radius 5. The equation of this object here is x squared plus y squared is equal to 25. Right, that's the equation of this circle. Now, this is not a function in the variable x, right? So this is not a function, and there are a few reasons for why that is true, but the main one is the fact that a circle does not pass the vertical line test. So here's our circle, centered at the origin with radius 5. And the reason I bring up a circle is because the idea of tangent line, the first time you all probably saw that was in geometry with circles, right? This would be a tangent line of a circle. This would be the tangent line of a circle. Now, but we know that the derivative of a function gives us the slope of the tangent line. And so the derivative gives the slope of the tangent lines. Well, if that's true, that we should also be able to use calculus and the ideas of derivatives to find tangent lines on a circle. So the question is, can we use calculus to find tangent lines on a circle, or anything else that might not be a function of x? So, or anything that may not be a function. And the answer is yes, we just use implicit differentiation. Okay, so the answer is yes, using implicit differentiation. Right, so how this works is like this. If I have this equation of a circle, x squared plus y squared is equal to 25, and we'll take the derivative of both sides with respect to x. Okay, so take the derivative. So this will be the derivative with respect to x of x squared plus the derivative with respect to x of y squared, which will be equal to the derivative with respect to x of 25. Okay, so we know the derivative with respect to x of x squared is simply 2x. The derivative of y squared with respect to x, well, remember, using the chain rule, this is going to be it's going to be 2y, right, times dy dx. So this is using the chain rule. Okay, is equal to the derivative of 25. Well, that's a constant, so this comes out to be 0. Now here we are making the assumption, right, that y is a function, or maybe not a function, sorry, let's say that y is an expression in x, but typically a function of x. I don't want to throw that word around here in this section. Now, I have this derivative here, dy dx. This is still the change in y versus the change in x. So this is still what I consider important. So we're going to solve for dy over dx. Right? We're looking for the derivative, and though this is not a nice function in terms of x, it's what we call an implicit expression, we can still find what we call the derivative of y with respect to x, right? The change, or the minuscule change in y versus the minuscule change in x. Okay, so I'm going to solve for this. So I'll move that 2x over, and I'll get that 2y times dy over dx is equal to negative 2x. Divide by y, or 2y on both sides, and we get that dy over dx is equal to negative, well, it's 2x over 2y, but it will be negative x over y. Okay. Alright, so let's look at what we have here. Back to our circle. Right, given this, using implicit differentiation, we found that dy over dx is negative x over y. Okay, now let's see if that matches the slope of our tangent lines. Okay, so let's look at the point. This would be 0, 5. Right? So let's look at the slope of the tangent line at 0, 5. Okay? So the slope of the tangent line of the circle, okay, is, well, that slope is going to be the derivative, okay, dy over dx, evaluated at the point 0, 5. Now here's some notation you may not have seen before, but basically if we want to evaluate the derivative at a point, what we'll say is we'll draw a big bar and put that point here at the base of it. This basically says evaluate the derivative dy over dx at the point 0, 5. Okay, so that means I'm going to plug in 0 into all my x's, 5 into all my y's. So remember, the derivative was actually negative x over y. So I evaluate that at 0, 5, and I get, plugging 0 in for x, 5 in for y, we get 0. Now this actually matches what we have here, because the circle has a horizontal tangent line at the point 0, 5. Right? It's very clear to see from the picture. Okay, how about we look at this point? Let's say that this is the point 4, -3. That is a point on this circle. This is probably not drawn to scale, but at the point 4, -3, right, we'll do the same thing. So at 4, -3, we get that the slope is the derivative evaluated at 4, -3, and that's going to be negative xy, or excuse me, negative x over y, evaluated at 4, -3, and that comes out to be, right, plugging the 4 in for x and the -3 in for y, we get a positive 4/3. Okay, which looks about right, actually. Positive 4/3, not quite a slope of 1, but almost there. And let's see what happens at the point here on this side of the circle, which would be -5, 0. Now, this is a vertical tangent line, right? A vertical tangent line. So what kind of slope should we see with a vertical tangent line? Let's think about it as we go to evaluate this. Okay, so at -5, 0, okay, the slope will be the derivative, of course, evaluated at -5, 0, which would be negative x over y at -5, 0, and we get, when we plug this in, -5, well, the whole thing's negative, so that'll be positive 5, let's say, over 0, which is, well, undefined. So what does that actually mean as far as slopes are concerned, right? You may have learned this as no slope, or the slope is undefined. And when the slope is undefined, this essentially means that you have a vertical line, which is what we already knew we should have given what we found here. Okay? So, yes, the answer to our question is we can still find the slopes of tangent lines, okay, We can still do that using the idea of the derivative, even if we don't have a function y equals something of x, right? We can still do it even if we have more complicated expressions, right? And some of you may be thinking, well, you know, if you had x squared plus y squared is equal to 25, well, couldn't you just solve for y, right, and get it to be a function of x? And the answer is technically we can, right? We can get that y squared is equal to 25 minus x squared. Okay, and to solve for y, we would take that y is equal to plus or minus the square root of 25 minus x squared. Now, here's the problem. We could go ahead and find the derivative of y, but we would have two pieces. Y is equal to plus or minus the square root. So we would have to do dy over dx is equal to the derivative. So really we could say plus or minus the derivative with respect to x of the square root of 25 minus x squared. Okay, which is going to be a chain rule, right? Going to be a chain rule. You're going to have a plus or minus. You have to evaluate things, and this is going to be way more complicated than what we had up here, which was just negative x over y. Okay, and more importantly, there are some examples where it's just not possible, okay, to solve for y in a nice sense. Okay, for example, if I had x cubed plus y cubed is equal to 3xy, okay, and I tried to solve for y, the problem is when I do that, moving this over, well, moving my y's over here, my x value over here, and if I factor out a y, well, I'm still left with y's on the inside here. Okay, so this is actually really difficult to solve for y. Okay, or possibly impossible to do by hand. Okay. In this case it's not, but we will see some cases where it is. All right, so this guy can't actually, we maybe could solve it by hand, y equals whatever, but actually, you know, it's not worth the trouble when we can still find dy over dx using implicit differentiation. Okay. And a lot of people seem to dislike implicit differentiation, but it follows just a couple of steps, right? One, you take the derivative of both sides. Okay. If you see a y, you apply the chain rule, which, remember, basically just means that you multiply by dy over dx. Okay, and then 2, you solve for dy over dx. And this is actually quite simple to do because this is always going to be a linear function. And what that means is that it's essentially you just move your dy dx's to one side, everything else to the other, factor, divide. I mean, it's typically that cut and dry. All right, so let's look at a couple examples, but this is essentially the two steps we will apply each time. Okay, and with a little practice, it will hopefully become somewhat second nature. Okay, let's start with the example we were just talking about. X cubed plus y cubed equals 3xy. Now, this function looks something like this. Okay, when it goes along. Definitely not a function, but still a pretty important function. I forgot its name, but it's used somewhere. There's an application somewhere. But anyway, the important part is that we want to find dy over dx, and we're going to use implicit differentiation. Okay, so that means you take the derivative of everything. So derivative with respect to x of x cubed plus derivative with respect to x of y cubed is equal to the derivative with respect to x of 3xy. Okay. Now, the derivative with respect to x of x cubed is 3x squared. And now, remember, whenever we take the derivative with respect to y, if we're taking the derivative of a y something with respect to x, we're going to use the chain rule. And that basically means we just use the power rule like normal, but we multiply by dy over dx. Okay. Now this is going to be equal to the derivative of this side, 3xy, and this is going to be a product rule. Okay, this is 3x times y, so it will be the derivative of the first piece, 3, and I'll go ahead and put in a 1 because that's the derivative of x, 1, times y left alone, plus, okay, now we're going to leave the first piece alone, and now it's going to be the derivative of the second piece, and the derivative of y all by itself, well, we could say it's 1, but with the chain rule we have to multiply by the derivative of y, right? Or you can just say that the derivative of y is the derivative of y. Okay, so let me go ahead and simplify this side. This is simply just 3y plus 3x dy dx. All right, so now I'm going to move things around. I want to solve for dy over dx. So all we're going to do is move it to one side or the other. So I'm going to move all my dy dx's to this side and move everything else to the other. Okay, so I'm going to get 3y squared dy over dx minus 3x dy over dx when I move that 3x dy dx over. And then I'll move that, I already have a 3y on this side, but I'll move that 3x squared over to this side. Okay, so now that I have all my dy dx's on one side and everything else on the other, I'm going to factor out this dy dx, right? That's the next piece. We're going to factor that out. And we could actually factor a whole lot more, maybe factor out some 3's, right? So let's see. So let's factor out a 3. And you know what? I'll just save that for later. So let's just factor out the dy over dx. And this is multiplied by 3y squared minus 3x And over here we have the 3y minus 3x squared. Right. Now we just divide. So once you factored, you divide. Okay, so I'll get that dy over dx is equal to 3y minus 3x squared all over 3y squared minus 3x. And here we can factor that 3 and get a y minus x squared over 3 times y squared minus x. Okay. And those 3's will cancel, so we get that dy over dx is equal to y minus x squared over y squared minus x. And there we go. Alright, so for this next example, let's say we have x squared plus xy minus y cubed is equal to 7, and we actually want to find the equation of the tangent line at 3, 2. So remember, if we want to find the equation of the tangent line, we need two things. We need the point, which we are given, and we need the slope. And we find the slope by finding the derivative. So we'll first need to find dy over dx using implicit differentiation. So that means we're going to differentiate everything in terms of x, right? So the derivative with respect to x of x squared, the derivative with respect to x of x times y, minus the derivative with respect to x of y cubed, and which will be equal to the derivative with respect to x of 7. Now the derivative of x squared with respect to x is just 2x, no problem there, hopefully. Now this next piece, this kind of throws students for a loop. For some reason, this is going to be a product rule because you have x times y. So it will be the derivative of x to start with, which is 1, times the second guy left alone, plus the first guy left alone times the derivative of the second, and the derivative of the second is dy over dx. Alright, then the derivative with respect to x of y cubed is going to be 3y squared, okay, times dy over dx, and that whole thing is going to be equal to 0. Okay. Now, what do we actually want to solve for? Well, we want to solve for dy over dx. So the first thing we're going to do is get it all by itself on one side. And it already is, so what we really need to do is move these guys over to the other side. Right, so we will do that. So this will be dy over dx times x minus 3y squared dy over dx. Often I factor during this step as well, since I know the next thing I'll have to do is factor. But in this case, I'll go ahead and write out each step individually. And this is going to be equal to negative 2x minus y. Right? Then we factor. So I get that dy over dx times x minus 3y squared is equal to negative 2x minus y. And then we divide. So we get that the derivative of y with respect to x is equal to negative 2x minus y all over x minus 3y squared. Okay, and that's the first part. We're actually asked to find the equation of the tangent line, and so we need to find this because this gives us the slope of that line, right? So the slope of that line we'll get from the derivative here. Okay, so if the derivative is, let me start up here, negative 2x minus y all over x minus 3y squared. Okay, that means the slope of this line I'm going to evaluate at that point 3, 2. Remember that point 3, 2 is actually given to us. Tangent line at 3, 2. Okay, 3, 2. Now I'm going to plug in the 3 and the 2. So this will be 2 times 3 minus 2. I'm just writing it all very explicitly here, just so you see what's going on. And this will be 3 minus 3 times 2 squared. Okay, so that'll be negative 6 minus 2 all over, that'll be 3 minus 4 times 12, or excuse me, minus 3 times 4, which will be 12. So what we will end up with here is negative 8 over, that'll be a negative 9. Okay. So we get 8/9 is our slope. Okay. So now that we have that, we then go to finding the equation of the line, right? We have that the slope is 8/9, the point is 3/2. You can either use the y equals mx plus b form, or another form you can use, which I haven't done in a lecture yet or in an example, so let me go ahead and do that. You can also use the point slope form, y minus y1 is equal to m times x minus x1, and you fill in the y1 and x1 from the point, and the slope, of course, from the slope. So you will get y minus 2 is equal to 8/9 times x minus 3 is the x value. Alright, so I'm going to move that 2 over and distribute this 8/9, so I will get that y is equal to 8/9 x minus 8/9 times 3 plus 2. And of course the 3 cancels here. And so I end up with y is equal to 8/9 x minus 8/3. And I have plus 2, alright, and which is going to be a 6/3 if I want that as a fraction. So I'll end up with y equaling 8/9 x, and that will end up being negative 2/3. So there we go. That is the equation of the tangent line for that, at that point, for that expression. Okay, for this guy here. Okay, so that's pretty involved because you got to solve to find dy dx in the first place. Then what you plug into is a bit more complicated, but at the same time you're actually given the point, so you don't actually have to find the y value. It has to be given to you. So there's also that. Okay, so let's look at another example. Alright, next example, I'll lay off the finding the equation of the tangent line for now, but let's say I have sine of y is equal to 2x plus cosine of y. Okay, so I'm going to take the derivative with respect to x of everything. And again, this is not a step you have to write, I'm just doing it. Just to be explicit, I guess. And then anytime I take the derivative of something with a y, I'm going to throw in a dy over dx. Okay, so the derivative of sine y, of course, is going to be cosine y times dy over dx. Okay. Then I move over to the other side. The derivative with respect to x of 2x is 2. Okay. And the plus the derivative of cosine y, which is going to be negative sine y, but remember we have to multiply by the derivative of the inside. Right? Then from here, remember we want to solve for dy over dx, so we're going to move all those over. So I like to move this guy over here just because that will be one less step. Right? So it will be cosine of y times dy over dx plus sine y times dy over dx is equal to 2. Then what should I do? Okay, I can't hear you, but you can go ahead and tell me. Factor. Yeah, so you're going to factor the dy over dx, and then you're going to divide. Now, again, a lot of people will kind of mix these steps together. Like I'll often factor as I move, or I might factor and divide all in one step instead of making it 2. But basically we have cosine y plus sine y times dy dx, I should say all times dy dx is equal to 2, and then we simply divide to finish this off. Okay, so dy over dx is equal to 2 over cosine of y plus sine of y. And that's it. Once you get this as dy over dx is equal to something, you're finished. And yes, you will end up with y's in your final equation. If you started with y's implicitly, you'll end up with y's implicitly. That's just the nature of how this works. All right, it's a very rare example to not see that. Okay. All right, let's look at the next example. All right, next example, a little more difficult this time. Let's say I have sine of x squared y cubed is equal to x minus e to the y. Okay, so what we're going to do here is go ahead and take the derivative of everything. Now I'm not going to write the whole d, over x for everything. We're just going to go straight to it. Here we need to be very careful, right? This is a chain rule. So the derivative of sine of stuff is cosine of that stuff. Right? Then times the derivative of that stuff. So the derivative of what's in here is going to go here, and that is going to be a product rule. Okay? Because you have x squared times y cubed. So it will be the derivative of the first guy, which is 2x, times y cubed, so the second guy left alone, then plus the first guy left alone times the derivative of the second, which will be 3y squared times dy over dx. Okay. So there we go. That's the whole derivative of the inside stuff. Then the derivative of x is equal to 1. And the derivative of e to the y, well, that's going to be itself. But remember, since that's a y, we're going to multiply by dy over dx. Okay. Now, there's one extra step here because, well, we have a dy dx trapped in here. We can't just start moving things. So first I'm going to distribute. So sometimes you will have to distribute things or simplify your equation before you start moving. But we'll distribute this cosine x squared y cubed. And I'm actually going to, I should put that in parentheses. I'm going to simplify this the writing of this one as well as I do that. So this is going to be cosine of, actually it usually looks better if we write the cosine at the end. So this is just going to be 2xy cubed times cosine of x squared y cubed plus 3x squared y squared cosine of x squared y cubed. This one has a dy over dx, and the whole thing is still equal to 1 minus e to the y times dy over dx. So all I did was distribute this cosine x squared y cubed. Now I can start moving. Alright, so I'm going to move my dy dx's over to one side, everything else to the other. It doesn't matter which way you do it, but I'm going to move this over here just so I don't deal with the negative sign, even though I will be dealing with one here, but it doesn't really matter. Alright, so I'm going to move this over, get 3x squared y squared cosine x squared y cubed times dy over dx plus e to the y times dy over dx is equal to 1, and when I move this over it will become minus 2xy cubed cosine of x squared y cubed. And then, of course, we're going to factor and then divide. And you know what? Since I have so much crap to write here, I'm going to factor and divide in one step. If I were to factor, I'd have this thing plus this thing, right? So this is going to end up being dy over dx is equal to 1 minus 2xy cubed cosine of x squared y cubed all over 3x squared y squared cosine of x squared y cubed plus e to the y on the denominator, and whew, there we go. That is the final answer. Alright, so a little complicated looking, but it's still the same steps. You just had a lot to write as you were going along. Right, so don't let that ever stop you. Okay, it's still the same process. Okay, for the next example, there's one specific thing I really want to show, is that sometimes you can simplify things to help you out. So for example, if I have x is equal to cosecant of xy plus e to the y squared all over 4x minus 3x squared, you might think if you just blindly went through and started taking the derivative, you'd get 1, and then over here you'd have to use the quotient rule, and then you would actually have to try and solve for dy over dx with dy over dx's in the top and the bottom of that fraction, and it would be a complete mess. Okay, a quicker way to go about doing this is let's multiply this on the other side, right? So this will be x times 4x minus 3x squared. Right, we're basically just multiplying both sides by this, and on this side it cancels. And so that the equation simplifies. Okay, so now what I really have is 4x squared minus 3x cubed is equal to cosecant xy plus e to the y squared. And now, no more quotient rule, and it's just your usual implicit differentiation. Okay, and this side is actually quite easy. This is just going to be 8x minus 9x squared. Okay, so it's going to be this side that will be a little trickier. Alright, so what's the derivative of cosecant of stuff? That's right, it's cosecant of the stuff, or negative cosecant of the stuff times negative cotangent of the stuff times the derivative of the stuff, and the derivative of the stuff that's going to be a product rule. Okay, and with implicit differentiation, right, that's going to be, well, the derivative of x, which is just 1, times y, so first piece will just be y, plus, okay, now x left alone times the derivative of y, which will be 1 times dy over dx. All right, then plus, so we have e to the y squared, so the derivative of e to the stuff will be itself, times the derivative of the stuff, and the derivative of of y squared, I'll go ahead and put in brackets just to stay consistent, it will be 2y, but since I'm taking a derivative in terms of y, or of a y term, I'll throw in a dy over dx. Okay, so this is like one of the previous examples where we need to distribute this thing, and then, before we can move stuff around. So this side will stay the same. It's still 8x minus 9x squared is equal to, let's distribute that, get negative y cosecant of xy, cotangent of xy, then minus x cosecant of xy, cotangent of xy, and this is a dy over dx term, then plus, ran out of room, e to the y squared, and actually let me write it like this, it should be plus 2y e to the y squared times dy over dx. Okay, so I'm going to move all my dy dx's to one side. Luckily they already are. And I'm going to move the other thing over to the other side. And while I do that, I'm going to go ahead and factor and move in this same step. Okay, so I will end up with 8x minus 9x squared plus y cosecant of xy times cotangent of xy, okay, is equal to negative, and I'm factoring, so it'll be negative x cosecant of xy, cotangent of xy, plus 2y e to the y squared, all times dy over dx. Okay, and let me grab another sheet of paper here to finish this off. Right, this is going to be, when I divide, finally, I'll get that dy over dx is equal to, I'm not going to mess with the top, it is what it has been. Right, 8x minus 9x squared plus cosecant xy, cotangent of xy, all over, and I'm going to rewrite the order of this just so it looks a little better. That's 2y e to the y squared minus x cosecant of xy, cotangent of xy. You'll see the book do this a lot. We typically like, if we have one negative sign, we kind of want it in the middle so it just looks like subtraction. Okay. Alright, so there you go. Pretty tough example, but one comment I got on evaluation one time was that I didn't do enough difficult problems during lectures, and I hope that you all agree that that's actually not true given this one. Okay. And let's do one more example. Okay, here we go. Let's say I have the square root of x squared plus y squared is equal to 2x minus y. What we might want to do to start off with is rewrite this as x squared plus y squared all to the 1/2, which is equal to 2x minus y. Okay, and then when I go to take the derivative, this is going to be a chain rule, right? Stuff to the 1/2, so that will be 1/2 times this stuff to the negative 1/2. Okay. Then times the derivative of the inside, and the derivative of the inside will be 2x plus 2y, but since I'm taking the derivative of a y term, I've got to multiply by a dy over dx. And on this other side, right, I'm going to say that this is just 2 minus, well, the derivative of y, which is just dy over dx. Okay. Now, one thing that's going to make this a little easier to deal with is because I want to, move my dy dx's to one side, divide by everything. If we rewrote this again, okay, move this underneath the fraction, this is essentially 2x plus 2y dy over dx all over 2 times the square root of x squared plus y squared, right? Because that 1/2 power is a square root, so when I move it down, that's going to be a square root. Now, I can also factor a 2 out of the numerator, so let's go ahead and do that, because that will cancel with this 2. Now, the reason I've done this is because I have a square root of x squared plus y squared on the bottom. I'm going to multiply both sides by that same thing. And the reason is because it's going to cancel this here. So I don't have that square root of x squared plus y squared in the denominator anymore. I've gotten rid of all my fractions. So now it's going to be x plus y times dy over dx is equal to, when I distribute this, it will be 2 square root of x squared plus y squared minus x squared, square root of x squared plus y squared dy over dx. Okay, now I'm ready to rock and roll. I've just got to move things around and factor, divide, all that fun stuff. So I'm going to move this thing over here and the x over here. Okay. And to show you how I do this and factor in the same step, when I move this over, I know it's going to be a plus square root of x squared plus y squared. So I will end up with a y plus the square root of x squared plus y squared on this side. Both of those are dy dx terms. You do this enough, you'll start to see this same pattern happening over and over again. And then on this side I have 2 square root of x squared plus y squared, okay, minus x when I move that x over. Alright, and now all that's left to do is divide. So dy over dx is going to be 2 times the square root of x squared plus y squared minus x all over y plus the square root of x squared plus y squared. And that, as they say, is that. So that's really the last example I wanted to look at, but these can get a little complicated, but really all you're doing, remember, is just take the derivative as you normally would, but whenever you see, or whenever you take a derivative of a y term, just throw in a dy over dx, and then when you get done, do whatever you can to finally solve for the dy over dx. And that is that. Alright, talk to you next time. Cheers.